Okay, the question of arc length. What's the arc length of this curve from, let's say, this point to this point? Now somebody said, well, it's going to be the integral of the velocity. And that's exactly true. It's a definite integral of the velocity from t equals 0 to t equals 3. Now we want to understand why it's the integral of the velocity. But just taking the fact that it really is the integral of the velocity, we can write out the integral that gives us the arc length of this curve. Just integrate our, and I said integrate velocity. That was not a good thing to say. We integrate the speed. We integrate the magnitude of the velocity. So we integrate the magnitude of the velocity, which I wrote down wrong. That should be 9 instead of 3. 4t squared plus 9. Can't really change a 9 to a 3, but it's going to look kind of bad. But that's 9. Okay, looks like a G, maybe a little bit truncated. And you do have to watch me for little errors like that. Okay, why would we integrate the speed to get the distance? Well, it comes down to the fact that if you have a constant speed, the distance you move is just the speed times a time interval. So if we're moving at 5 units per second for 3 seconds, we move 15 units. This is an obvious idea. Okay. Now, a little more formally, because this isn't a constant speed, is it? This is clearly a non-constant function. To see why this works, we start with the fact that our time goes from 0 to 3. And anytime we set up an integral, we want to identify our independent variable and the interval over which we're going to try to determine whatever it is we're trying to determine with respect to that independent variable. So our independent variable is the time. Time goes from 0 to 3. That's our interval. We want to partition that interval, which means break it into little pieces. The reason we do that, on each little piece, this velocity, while it's going to be changing a bit, changes very little. If our interval is small enough, we can make this velocity as nearly constant as we wish. It'll never really be constant, but it's going to be nearly constant, and then we're going to do a limit and do away with the entire effect of the non-constant velocity. Okay, so we partition the interval, and the way we write that down, you would have done Riemann sums in an engineering calculus course, if you had a real engineering calculus course, which you would if you'd taken the course on campus here and at many other community colleges. So our interval goes from 0 to 3, so we said, okay, t0 is 0, and 0 is then going to be less than t1, less than t2, etc., for some undetermined number n of points, with the last of these points being 3. So t0 is 0, tn is 3, and we have n points in between. Actually, n minus 1 points in between, but we've divided into n intervals. First interval from 0 to t1, second interval from 0 to t2, and so on and so on. Last interval from t sub n minus 1 to t sub n. And this is something you should be very familiar with starting a multivariable calculus course or vector calculus course. Having done that, we can say that, and I'm being a little fuzzy because I'm just doing this kind of conceptually, that on an interval between t sub I and t sub I plus 1, if we make our intervals small enough, and we can make them as small as we wish, the magnitude of our velocity, that is our speed, changes very little, so that the magnitude of v of t, our speed, times the delta t being the time between t sub I and t sub I plus 1. So delta t could be written t sub I plus 1 minus t sub I, but we understand that's a delta t. so that this product, the speed times delta t, is very close to our distance, okay? And I just wrote that is the distance. And I'll write or very nearly so. Now you really do need to understand how to do Riemann sums and how to partition intervals. It's a skill that you should have developed to some extent in the application section, especially of your engineering calculus course. And it's a skill that we're going to be building on in this vector calculus course. Now, the curve we've drawn here is in the xy plane. It's in 2 dimensions. We can extend everything that we've done here to higher dimensions. Okay? We can extend to 3 dimensions, and we do that here. And we can actually make some sort of a sketch indicating what the curve might look like in 3 dimensions. And we'll talk about that in the next video, and a little bit about even extending to higher dimensions, although in this course we pretty much confine ourselves to 2 and 3 dimensions.